Hello everyone. Welcome to the fourth episode in my op-amp tutorial series, the Integrator and the Differentiator. In the previous episode, we introduced the tenets of the ideal op-amp, as well as the non-inverting op-amp configuration and the inverting op-amp configuration. If you haven't had a chance to watch the previous episodes, you can check them out on my channel. Thus far, we've only discussed circuits that have a constant gain for all frequencies, but oftentimes it is useful to reshape a signal with a circuit by amplifying some frequencies and attenuating others. Today we'll introduce two circuits that perform functions like that, the integrator and the differentiator. Here's the schematic for the integrator circuit. This circuit has the op-amp in inverting configuration, except with a capacitor in the feedback loop rather than a resistor. First, we'll derive the expression for the output voltage, Vout, of this circuit. Then we'll discuss the attributes and applications of this circuit. We have grounded the VOP plus input, as we did in the purely resistive inverting amplifier configuration from the previous video. I have left the input resistor labeled R2 for simplicity, even though it is the only resistor in the circuit, because the previous video had R2 in that position. I have left in a box in the lower left corner the tenets of the ideal op-amp to remind us of the rules we must follow that allow us to solve for these circuits. Since the input impedance of this amplifier into the VOP minus input is the same as in the purely resistive inverting amplifier configuration, the expression for In is also the same, so we pull that equation from the previous video. We see that the current into the resistor R2 is proportional to the input voltage Vin, but to calculate the voltage across the capacitor, we need to use the capacitor current voltage relations. Here we see that the voltage across the capacitor is proportional to the charge stored in it, so we can think of In as charging up or discharging the capacitor, depending upon the sign of the current. And since current is the derivative of charge with respect to time, we can see that it is proportional to the derivative of voltage with respect to time. In other words, Vin signals that change more slowly will tend to produce very high voltages across the capacitor, because the capacitor will look more like an open circuit to In. And Vin signals that change more quickly, In will tend to see the capacitor more as a short circuit, and so the voltage drop across it will tend to be small. Thus, slower signals will tend to be amplified more than faster signals. Applying this to the circuit and rearranging terms, we get an expression for the derivative of the capacitor's voltage with respect to time in terms of input current and capacitance. To calculate the voltage across that capacitor, rather than the time derivative of the voltage, we have to integrate both sides of this equation with respect to time. Pulling out the capacitance term, which is a constant, we have Vc1 equal to 1 over C1 times the integral of the input current. Now we substitute in the expression for In from the purely resistive inverting amplifier configuration equation, and simplify to get the voltage across C1 in terms of Vin and the component values. Finally, we note that C1 is actually connected to the VOP minus virtual ground on its positive side, due to the direction of current In, and so Vout is actually 0 volts minus Vc1, which is equal to negative 1 over R2C1 times the time integral of Vin. So here's our expression for Vout of our integrator. In the time domain, as we've expressed it here, there isn't really an expression for gain as with previous circuits. Since the output is not proportional to Vin, it's proportional to the integral of Vin. This kind of circuit can be useful for filtering signals with unwanted fast-moving content or garbage that should be ignored, dulling signal edges by attenuating the high-frequency content, or for implementing the I portion of a PID control loop in the analog domain. In the past, it was also used as an integral calculator, where the input signal was the function that you wanted to know the integral of, and the output voltage versus time was measured to see the result. While the time domain analysis of this circuit is illuminating and instructive, it is generally more useful to analyze it in the frequency domain, which we will do now. So, in the frequency domain, the most straightforward analysis is to take the equation we derived from the resistor-based inverting amplifier from the previous video, and recognize that this expression will work for any impedances for the positions in the circuit that R1 and R2 occupy, be they resistive, capacitive, inductive, or otherwise. So all we need to do is replace the resistance of R1 with the impedance of capacitors C1, We will call this impedance ZC1. The impedance of capacitor C1 is 1 over C1s, where s is the Laplace transform variable we use when discussing frequency responses, equivalent to j omega or 2 pi jf. Substituting this into the equation from the purely resistive inverting amplifier and simplifying, we get a gain of negative 1 over R2 C1s. This is a pole at zero frequency. So, taking a moment to look at this transfer function, we can see that the magnitude of the gain at a given frequency gets higher the lower you go in frequency, which of course we could tell from the time domain version. This means the gain is extremely large for very low frequency signals. This presents a problem. Small DC offsets that appear in all op-amps will cause the output to rail after a certain period of time as they are integrated. These offsets are impossible to eliminate completely and are very important non-idealities that I will explore in detail in later videos. Additionally, the integral doesn't specify a starting time point, which means it's always integrating when the op-amp is powered, and powering up an op-amp produces some unclear initial conditions that could vary greatly from op-amp to op-amp and power-up scheme to power-up scheme. So complications in real op-amps are significant enough that we should address them to some degree even now in this ideal op-amp world. There are a few ways to mitigate these effects, which we will explore now. One way to fix this issue is to add a resistor in parallel to the capacitor C1 to place a limit on the maximum gain for any frequency. This effectively changes it to a purely resistive inverting amplifier at low frequencies and an integrator only at high frequencies. Let's derive the transfer function of this integrator with feedback resistor to see how it is different from the pure integrator. The resulting impedance in the feedback loop is now 1 over C1s in parallel with the newly placed R1. Let's call it ZFB since it's in the feedback loop. Simplifying this equation, we come up with the following expression for ZFB. And substituting it in for R1 from our inverting amplifier gain equation, we get the following transfer function for the integrator with resistor. This has a pole that occurs at a frequency of 1 over R1C1 radians per second and a proportionality factor of negative R1 over R2. Let's take a look at what this equation looks like at low and high frequencies and see if we can come to some useful approximations. For frequencies much lower than 1 over R1C1 radians per second, we know that means that R1C1s is much less than 1, which will cause the denominator of the transfer function to be approximately 1, since a number much smaller than 1 plus 1 is approximately 1. I recognize that since we're dealing with a real pole, that R1C1s is purely imaginary, but this doesn't really affect our approximation methodology as the results are the same, and thus treating the values as complex is an unnecessary complication, pun intended, when calculating this kind of approximation. This results in an approximate gain that has no frequency dependency and is identical to the purely resistive inverting amplifier configuration. Conversely, when we examine frequencies much higher than 1 over R1C1 radians per second, we see that in the denominator of the transfer function, R1C1s is much larger than 1, and thus the denominator approximates to R1C1s, which, when simplified, results in an expression that is identical to the purely capacitive integrator. So we can see here that if you only need the integrator to work for a certain frequency band, and don't need it to be particularly high gain at low frequencies, you can set the values for C1 and R1 to create two regions of operation, one at low frequencies that has a constant finite gain, and one at high frequencies that acts as an integrator. This limits the degree to which low frequency effects can change the output voltage, and permits the integrator to produce more practical output voltages. An alternative to this, if a true integration is required over a specified time interval, the resistor can be replaced with a switch, either solid state or electromechanical, to reset the capacitor by shorting it out prior to the integration interval start. This effectively converts the integral from integrating from when the circuit was most recently powered up, with some dubious initial conditions as mentioned previously, to an integral that starts from when the switch was most recently opened. The component values can be set to ensure that the output voltage does not get close to the rails during the desired integration interval. Before we move on from the integrator, a practical limit for the integrator gain is still the real op-amp's gain. So even without the resistor in the feedback loop, the integrator will be limited by the maximum open-loop gain of the op-amp, which, while high, is not infinite, so deviation from a pure integral will occur over long stretches of time even with no feedback resistor. Now we'll discuss the differentiator, which is sort of the opposite of the integrator. As you might expect, the differentiator looks very similar to the integrator, except with the capacitor and resistor swapped. Again, we'll derive the output voltage first, then discuss the properties of the circuit. With the differentiator, you don't get to use the expression for input current we pulled from the purely resistive inverting amplifier configuration, so we recall that due to the virtual ground in the inverting configuration, the input circuit is simplified to Vin connected to a capacitor to ground. And looking at the capacitor current and voltage relations again, we note that the current through the capacitor is equal to the capacitance times the derivative of the voltage across it, which in this case is the input voltage with respect to time. Now to get the voltage drop across R1, we just multiply that capacitor current by R1. And to get Vout, we account for the way VR1 is oriented with respect to VOP minus, and we get our transfer function. Vout equals negative R1 C1 times the derivative of input voltage with respect to time. Similar to the integrator, there isn't really an expression for gain for the differentiator in the time domain as with previous circuits. Since the output is not proportional to Vin, it's proportional to the time derivative of Vin. Differentiators are useful for filtering signals with slow-moving noise, garbage that should be ignored in the low-frequency regime, eliminating DC offsets, sharpening edges by amplifying the high-frequency content, or for implementing the D portion of a PID control loop in the analog domain. In the past, it was also used as a derivative calculator, where the signal was the function you wanted to know the derivative of, and the output voltage versus time was measured to see the result. Now we look at the more useful frequency domain representation of the differentiator. We again take the purely resistive inverting amplifier equation and replace R2 with the frequency domain impedance of the input capacitor. Substituting in this impedance into the equation, we get the following expression for Vout and the gain. We see that the magnitude of the gain at a given frequency gets higher the higher you go in frequency, which of course we could tell from the time domain version. This means the gain is 0 at DC and gets large for high-frequency signals. This doesn't have the same issue that the integrator had, as all offsets are ignored since the gain at DC is 0. However, a problem does occur at high frequency. Recall that the input impedance of the resistor-based inverting amplifier is simply the input resistor's value. For the differentiator, this has been replaced with a capacitor, and so the input impedance is now the capacitor's capacitive reactance. At high frequencies, this can get extremely small, down to milliohms, depending upon the frequency and capacitance. And so it is usually swamped out by the input signal's source resistance before the capacitive reactance can get that low. So it is therefore useful to look at what happens to the gain when a source resistance is added in series with the input capacitor. Here we're going to use the name Vs for the source voltage, as this is a more common name for the voltage when incorporating the source resistance. So we'll start again with the inverting amplifier equation, with Vs in place of Vin. But this time, the impedance we need to compute is the combination of the source resistance in series with the capacitive reactance of C1. We'll call this combined impedance Zin. Simplifying Zin and substituting it into the inverting amplifier gain equation, we get the following expressions for Vout and the gain. Here we see that the equation results in a 0 at 0 frequency and a pole at frequency 1 over Rs C1 radians per second. This indicates that the circuit will act like a differentiator at low frequency, but as that pole comes into play, it will cancel out the 0, and the resulting circuit will be at a fixed gain at high frequencies. Let's look at these two frequency regimes to see what the approximate gain is for each regime. First, we'll look at frequencies much less than 1 over Rs_C1 radians per second. Under these conditions, the quantity Rs_C1s is much less than 1. And so, Rs_C1s plus 1 is approximately equal to 1. This completely negates the denominator of the transfer function. and results in an approximate gain of negative R1C1S. So at low frequencies, we get the same result as the pure differentiator without Rs. This tallies with our intuition that at low frequencies, C1 is a high impedance. So if we want a pure differentiator, so long as the frequencies are much lower than 1 over Rs C1 radians per second, then the circuit will act like a pure differentiator. Now we look at when frequencies are much greater than 1 over Rs C1 radians per second. Under these conditions, the quantity Rs C1S is much greater than 1, and so the denominator of the transfer function becomes approximately Rs C1S, which, when simplified, reduces to the purely resistive inverting gain with Rs in place of R2. This makes sense intuitively because at high frequencies we can think of C1 as a short circuit, and thus it's really just Rs and R1 in the resistive inverting amplifier configuration. So here we see that this modified differentiator acts like a pure differentiator at low frequencies, and like the purely resistive inverting amplifier configuration for higher frequencies, which is generally sufficient as most circuits have a finite bandwidth they wish to operate on, and you can never operate on an infinite bandwidth. All real-world signals are band-limited. It's important to note that while the ideal op-amp has infinite bandwidth, real op-amps do not, and depending upon the op-amp being used, as well as the values for Rs and C1, the op-amp's finite bandwidth may limit the range at which the circuit behaves like a differentiator before the pull from Rs-C1 comes into effect. And so this relationship only holds for some circuits. And of course, real op-amps do have finite bandwidth, and so the relationship will not hold for sufficiently high frequencies no matter what the op-amp is. That concludes this episode. Today we introduced two op-amp application circuits that apply different gains at different frequencies, the integrator and the differentiator, as well as deriving their respective transfer functions in both the time and frequency domains. We also identified a common low-frequency problem with integrator circuits, and how to mitigate that issue and adjust the transfer function accordingly, and a common high-frequency problem with differentiator circuits and how to adjust the transfer function to capture that effect. In the next video, I'll be doing lab demos of the circuits we discussed in episodes 3 and 4 to see how they behave in the real world. Thank you for watching my video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave them in the comments. See you next time.